Hello, linear algebra student. This video is for chapter 4.3, part 4. We're going to find the basis for two commonly known space, null A and column A related to a matrix. So in 4.2, we figure out how to define null A, which is the set of vectors that maps into zeros, right? So if A is what is given, AX equal to 0. So these are all the vectors that that A maps to 0. So we call it null A. And it turns out that this is a vector space. And because it's a vector space, we can find the basis, right? So we want to find the linear independent set of the basis. So the first step to do that is actually to find what are the null A, right? So this is just referring to 4.2. To do a null A, you actually have to solve it. And so you would do REF of A. So this particular one, they give us a REF, but it is not enough because to solve null A, we actually have to solve all the way to the REF of 1 0 0 2 1 0 1 1 0 0 0 0, right? So that would equal to I have it already. Oh well, actually I didn't do the zero column, but it's just or 0, right? So pretend we solve it, and then when we do REF of A, so it's 1 0 negative 1 0 0 1 1 0. 1 0 negative 1 0 0 1 1 0 0 0 0 0. That means this the one that maps to it would be x1 is equal to x4. No, x1, x2, x3. x1 equal to x3. x2 is equal to negative x3, right? Because x2 plus x3 equal to 0. And then x3 is free. So what happens would be, right, in parametric form, we have x1, x2, x3 would equal to x1 would equal to x3 times what? 1, negative 1. x3 is 3, that means this is x3, right? So this x1 and x3 is the same. So all the vectors that maps to 0 would have this form. That means you pick whatever x3 you have and you multiply to 1, negative 1, 1. That would be the vector. So if that is the case, all the x1, x2, x3 in null A would be a kind of like a multiple of this vector. So the basis is that vector. 1, negative 1, 1, because x3 is free, so just give anything of it, and this would be the solution set of having A times x equal to 0. So this is the basis for null A. So to do that, you actually solve for the parametric form, and then the vectors is the parametrics, is the basis. Another subspace that comes out of a matrix is column A. So column A is actually the linear combination of all the columns in A. So if A is reduced in echelon form, each prefix columns of the REF are actually linear independence because no vectors is a linear combination of the vector before it. So the same column of A are also linear independence. So so we have this theorem saying that the prefix column of matrix A would form a basis of column A. So if you only look at the prefix column, which you don't need REF, so you would just have a. So in this case, it is already in REF. Do you see? This is a prefix column. This is a prefix column, right? Because you can write x1 equal to x2. Oh, Yeah, so if you after you do an REF, then this would be done, it will be gone. So these two are basically independence and also would be the basis for column A, and that is the theorem. So I'll talk about how to prove this, and basically it's kind of the same idea that I talked about earlier. But so for the time being, if you are to find the basis, so this would be the two bases for column A, because column A is just a linear combination of all these vectors, and if these are free variables, that means I can actually write this as a combination of these two. Right? So column A's basis would be very easy, would equal to this 1 0 0 and 1 5 0. I don't really need to do the RREF. Now, to do the basis for now A, I need the RREF. Okay, RREF of A, because I want to write the parametric form. So I already did it in the decimal matrix. 1 0 0 2 0 0, right? 2 0 0 1 5 0 2 negative 2 0 1. So I will do a B. Actually, strictly speaking, I should do a 0 0 column, but it's not particularly interesting. But because I actually am solving AX equals 0 for now B, now A. So when I do B, so the answer is 1 2 0 11 over 5 0. 1 2 0 11 over 5 0. How come that's semi? One oh is it the wrong one? 1 2 1 2 1 5 2 0 1. Yeah. Okay, so because it's 4, yeah. Okay, so solve A. So do now A. So that is to do AX equal to 0. So this is not the REF of A, it's REF of the augmented matrix, which is the next one is 0 0 1. 0 0 1. What is it? Negative 1/5 0. And the last row is all 0. So you can tell that x1, x2 is free, x4 is free. x1 is negative 2 x2 minus 11 over 5 x4. x2 is free. x3 is 1/5 x4, and x4 is free. Right? So if that is the case, what is x1, x2, x3, x4? Just remember to do now A. We would say, okay, we can factor the x2 out because it's free, so that's x2. So x2 shows up where? Negative 2, and then 1, and then no more x2. Plus x4. The first one is negative 11 over 5. And then the second one don't have x4, and then I have 1/5, and then a 1, right? Second is 0. So you can see that all of these now that maps to 0 are a linear combination of these two vectors, having x2 and x3 being the free variable. So the basis for now A, it takes much longer to find out A, is negative 2 1 0 0, and also negative 11 over 5, 0, 1 over 5, and 1. So this is the basis for now A. You use this, it would all of them would map to 0. Example 2, do one more. So I want to do the basis for now A and column A. So let's do now A first. Well, let's do column A first because column A is so easy to do, right? Column A basis, because I don't even need REF. I just need the prefix column. I have three prefix column. This prefix column will be the identity or the independent row. Now, in these two examples, my matrix is already in REF form, so you don't have to do anything. But in case it is not, you at least need to do REF or REF. Select the three column and go back to A to get the matrix, to get the list. So the basis of column A would be 1, 0, 0. I'm going to do this again do another example during the lecture. So 4, 5, 6, like that. Okay. It just happens that this is already in REF form, so I just copy it. If you have to do some work to do REF, your columns that are independent are the one that you before the REF. Okay. What about now A? Now A, I have to do some work, right? I have to solve AX equal to 0. And so that means I need to do 1, 0, 0, 2, 3, 0, 4, 5, 6, 7, 8, 9. This seems to be a 0, 0, 0, and reduce it. I have it in C. I just need to add a column of 0, 0, 0, 0. And then I do a row reduction echelon of C. It would be 1, 0, 0, 2 third, 0. And then 0, 1, 0, 1, 6, 0, 1, 0, 1, 6. Also 0. 0, 0, 1, 3 over 2, 0, 0, 1, 3 over 2, 0. Obviously, the three prefix columns is the same as here, so x4 is free, right? Let's write it out. x1 equal to negative 2 thirds of x4. x2 equal to what? 1/6 of x4. x3 equal to 3 over 2 of x4. And you can say and x4 is x4. So the solution for now 3x4 is a linear combination of just pick one x4 and it's always 2 thirds, negative 2 thirds. I should say negative 1/6, right? Negative 1/6, 3, is it? Is it negative? Yeah, also negative 3 over 2, and then 1. So it's always a linear combination of the x4 of this vector. So the basis would be what? That vector. Anytime you have a vector that is a multiple of these, it would maps using A, it would maps to 0. Okay, so that's it for chapter 4.3. It's quite long.